we'll be calculating the VO2 max of an orange. And although Garmin, you can kind of trick it into calculating the heartbeat for this orange, it won't give you a VO2 max score, but we can use some high school chemistry to get an estimate of what the VO2 max score of an orange would be. If you don't know, VO2 max is essentially an indicator of aerobic fitness. So the untrained adult male might have a VO2 max of 35 to 40, while trained athletes might exceed 60, and the highest ever recorded VO2 max by a triathlete, Blumenfeld, was 101. So crazy stuff. But VO2 max is how much oxygen your body can consume maximally. So what is the maximum rate of oxygen that you can take? And it's in the units mg per kg per hour. So how would we begin to calculate the VO2 max of an orange? Well, scientists have done experimentation, and they have calculated that at room temperature, or 20 degrees Celsius, 293.15 Kelvin, a sweet orange releases 12 milligrams of CO2 per its body weight, kg, per hour. Now that's a critical piece of information to calculate the VO2 max, because how would a fruit like this consume oxygen? How would we determine that? Well, there's a well-known equation for cellular respiration. To stay alive, the orange has to convert simple sugars, so C6H12O6, that's glucose. It uses up the oxygen. That's how we're measuring its aerobic fitness. And then CO2 to produce carbon dioxide and water. This equation, it's balanced, is known as cellular respiration. And you can see that the moles of O2 going in are the same as the moles of CO2 coming out. So this tells us that VCO2 equals VO2. And that means to calculate the VO2, we only need to look at the VCO2, which we can calculate after a bit of work from this critical piece of information here. So in order to investigate this, it's more helpful to convert the milligrams into moles. So we know that carbon dioxide, it's 44.01 grams equals 1 mole for carbon dioxide. So to convert this to moles, it's essentially just 12 divided mg. Notice that this is g, so we have to convert 44,010 mg. Cancel. That's the number of moles of CO2 per kg per hour. Alright, this value is approximately 0.002727 moles per kg per hour. Alright, and now we can use the ideal gas law to find the volume. We have the equation PV equals nRT. Well, P is pressure. We'll keep that at 1 atmosphere. V is what we're trying to solve for. N, that's the number of moles, which we just calculated that an orange produces per kilogram per hour. R is the ideal gas constant. I think it's around 0.08 atmospheres for every mole times. Okay, so it's a constant. And then T is the temperature, and we're taking room temperature, so that's 20 Celsius, or we're going to use 293.15 Kelvin. The units are always supposed to be in Kelvin. So plugging all of these known values in, you should get that V equals 0.00656 liters, or roughly 6.56 milliliters of O2 per kilogram per hour. And VO2 is typically displayed in kilograms per minute. So to get the VO2 of an orange, we simply divide by 60 minutes, and then that gets us the VO2 of an orange is roughly around 6.56 divided by 60, which equals 0.109 milliliters divided by kg per min. Alright, that is a very low VO2, so the orange is a pretty aerobically unfit fruit. Maybe after some training it can develop its VO2, but that has yet to be tested. Alright, thank you.